Hello and welcome. So with this question, we're going to be given a simple basic Cobb-Douglas production function with a certain parameterization. Alpha is going to be equal to 0.3. And then we're going to find the fraction of income that capital and labor receive. So like the labor share of income and the capital share of income. And then we're going to give a little shock to labor. You know, there's some increase in labor, and we're going to see how total output, rental price of capital, and the real wage change. If you want to skip ahead, I'll try to put links in the video description for you to skip ahead to like a specific question you might have. So a Cobb-Douglas production function takes the following form. So y, or output here, is equal to, you got A, that's a kind of technology, that's not a factor or input, that's a technology that often people just have scaled to 1 and doesn't change. So A, got capital raised to the alpha, and then labor raised to the 1 minus alpha. So here is a simple Cobb-Douglas production function. This is a constant returns to scale production function. Cobb-Douglas is actually a bit more general. I'm pretty sure you could change these values quite a bit. You could also add a bunch more factors in here, but at its simplest and easiest, this is a Cobb-Douglas production function. We're being told that alpha is 0.3, so you can imagine this being set to 0.3. And then 1 minus alpha, so 1 minus 0.3 is 0.7. So this is the production function we're dealing with. In solving this problem, it's nice to say general, so I'm going to leave in alpha above k and 1 minus alpha above labor, just because it's nice and easy. So the first question here asks, what fractions do income do capital and labor receive? So the cool thing about a Cobb-Douglas production function, when you have constant returns to scale, when these two exponents here sum to 1, so alpha plus 1 minus alpha sums to 1. When that happens, I know that capital share of income is going to be alpha. So I know the capital share of income is going to be 0.3, and then I also know that the labor share of income is going to be equal to its exponent. 1 minus alpha is 1 minus 0.3, so I know it's going to end up being 0.7 just by looking at this. But we need to show, probably on an exam or homework or something like that, you're going to actually want to have to show how to do this. So let's do capital first. So what is capital's share of income equal to? Capital share of income is equal to, so you have some total amount of income or production, which we have labeled here like notation wise as y, so that's production, and some portion of it is going to go to capital. So there's a certain quantity of capital called k here, so that's the quantity of capital, and then how much does each unit of capital get paid? Well, that's going to be equal to the rental rate of capital. So you have the rental rate of capital times the quantity of capital. That's the total amount of money going to capital divided by production, which is also like the total amount of money that could go anywhere. So this is going to be capital share of income. Actually, let me get to capital share of income in a second. I'm going to do labor share of income. Because it's a little bit more intuitive. So once again, there's some total amount of income, y, that's equal to real income or production in this production function. And there's a certain quantity of labor, that's how many workers there are, L. And each worker gets paid a real wage equal to W. So each worker is getting paid W, and there's this many. So that means this is equal, W times L is equal to like all the wages getting paid to all of those workers. So that's how much cash is being paid to workers. And y is how much cash there is to be paid to anything. In the Cobb-Douglas production function, there's a certain amount of production, and that money has to go somewhere. So part of it's going to go to capital, part of it's going to go to labor, and all of it's going to go to one or the other. The question is how much goes to one, how much goes to the other. So to find that, we're going to have the wage rate times the total quantity of labor divided by production. Awesome. So first off, what's the wage rate? Let's get to this in a second. So let me do that above. So wages. So real wages in the book, we're given this, and let's just go with what we're given. Real wage is the first derivative output with respect to labor. So I'm just going to take the production function and take the first derivative of it with respect to labor. And that is, in other videos, I walk you through step-by-step how to do this. So I'll give a link to those other videos, or you can find them yourself. But I know it's going to be equal to the following. So right here, this is the marginal product of labor. So MPL, which is how production changes given a change in labor. So like if I were to add 1 unit of labor, how much does production go up? It's equal to this little equation right here. Awesome. So that's W, the wage rate, marginal product of labor, times how much labor there is divided by how much production there is. And you can see there's quite a bit of room for things canceling out. So let's just kind of reorganize this a little bit to make that clear. So you got 1 minus alpha, and then y is up top, y is down here. So you got y divided by y, and then you got L here. I'm just doing algebra right now. And then L is in the denominator inside the parentheses here, so L goes down. So these two cancel out nice and cleanly. And all we're left with is 1 minus alpha. So the labor share of income, which is defined by this little equation, is going to be equal to 1 minus alpha. Great, good job. Okay, so now let's do the capital share of income. So the capital share of income is going to be the rental rate of capital times the quantity of capital divided by total production. So what's R? That's the rental rate of capital, which is equal to the marginal product of capital. And the marginal product of capital is going to be how production changes, di y, given a change in capital, di k. In other videos, once again, I walk you through step by step, given the Cobb-Douglas production function, how to find this. But I know that it's alpha times total production divided by capital. So it's alpha times y over k. So I'm going to take our little equation here for capital share of income. I'm going to plug in what I know R is, times quantity of capital, all divided by total production. And you can see it's very similar to this stuff up here. There's a lot of stuff going to cancel out. So you got alpha, you got y, the bottom, y is up top, times you got this k here up top, and the k in the denominator inside those parentheses goes to the bottom. So all of these things cancel out. So capital share of income is equal to just alpha. Yep, so these are our answers. Labor share of income is 1 minus alpha, and capital share of income is just alpha, given this production function. So what is alpha? Alpha is equal to 0.3, and then what is 1 minus alpha? 1 minus alpha is 0.7. So the answer is 0.7 and 0.3. So now let's get to problem B. So B says, suppose that immigration increases the labor force by 10%. What happens to total output in percent? And what happens to the rest of the things that we figured out? Okay, so let's bring that down here. The first thing I like to do, given a problem, is to organize what we know already. So we know that alpha equals 0.3. We also know our production function takes this form. It's a Cobb-Douglas production function. We also know a couple things. Initially, for example, labor shares, the marginal product of labor was this guy over here. Initially, the marginal product of labor was this. So I'm adding a little subscript, MPL sub naught, to show like the first version was equal to 0.7 times this. And then initially, the marginal product of capital initially was this. Okay, so let's do this. Oh, yeah. One more thing. Initially, labor was this, and now labor has gone up by 1.1%. So new labor is equal to 1.1 times old labor. That is to say, labor has gone up by 10%. Okay, so now that we got our setup, initially production was this. So production at y sub naught was here. And now production has gone to the following. But what is new labor equal to? It's just this equation right here. So our new production level is equal to these first parts are the same, technology and capital is the same, and then 1.1 times the initial labor raised to that exponent. We can move this 1.1 to the front. And then everything else is exactly how it was before. So what is 1.1 raised to the 1 minus alpha? 1.1 raised to the 1 minus alpha is equal to, give me a second. Remember, 1 minus alpha is equal to 0.7. 1.1 raised to that is equal to 1 raised to the 0.7 is equal to 1.069. And then this portion right here is just old production. So I'm just substituting that in. So given the increase in labor, the new output, so given the new increase in labor, our new output is just old output increased by 6.9%. So output is up by 6.9%. Good job. Let's do the rental price of capital now. So the rental price of capital in our notation is just R, and R is equal to the marginal product of capital. So the real rental price of capital is equal to the marginal product of capital. Marginal product of capital is just the first derivative of all this. It's actually, we have that little equation over here. Oh, here it is. So let's do R sub naught is equal to our old one. Where is it? There. And then our new rental rate of capital, and then have subscript sub 1 is equal to all of this with the new values. So, so here's our initial rental rate of capital, alpha times y to the k. Here's our new rental rate of capital, alpha times y to the k. The thing is, given the increase in labor, labor's gone up by 10%, we know that output here is going to increase. So that's output sub 1. And output sub 1 is equal to a 6.9% increase in initial output. So that's 1.069 times the initial output. So we can simplify this. To the following. So it's 0.069 times our initial rental rate. So I could just substitute that in. So that means the rental rate of capital has gone up by 6.9% as well. So our rental rate of capital has gone up by 6.9%. How we figured that out is we took the initial rental rate of capital, we then plugged in the changes. Alpha is the same, nothing changed with alpha, that's still 0.3. Capital is the same, we're told nothing changed with capital, but output definitely has changed. We just found that output changed by 6.9%. So plugging that in and simplifying, we see that the new rental rate of capital is 1.069 times the old rental rate. So that means the rental rate of capital has gone up by 6.9%. Lastly, we're going to do the real wage now. So initially, real wages we found were equal to this equation. And now new wages are going to be equal to old wages with these new levels for output and labor. So you have 1 minus alpha. Y is now y sub 1. And labor is now labor sub 1. So y sub 1, like new output, is equal to 1.069 times our initial output. And then labor is increased by 1.1% times the initial. So we need to pull out the 1.069 and the 1.1 out to the front. Divided by 1.1, and we could remove all that. And that simplifies to the following. What's 1.069? Let's see. .069 divided by 1.1 is 0.971, or let's just say 0.97. And then what's 1 minus that? So that's 2.8%. So real wages are 0.97% of initial wages. So that reflects wages have gone down by about 2.9%. Cool. So hopefully that was helpful. Hopefully that was clear. You can see all we did, the initial thing that we had was a labor force increase by 10%. So starting off with production, we increased labor force by 1.1%, by 10%. So we times the initial labor by 1.1. We pulled that out, including the exponent, to find out that output increased by 6.9%. We then turn our attention to labor price of capital. Given that output is increased by 6.9%, that implies that the rental price of capital has also gone up by that amount. And then turning to the real wage, starting off with the initial real wage of this, we know that production's changed, we know that labor's changed. Production changed by 6.9%. Labor increased by that 10%, so it's 1.1%. Combining all that together, we see that real wages has gone down by 2.9%. So intuition-wise, suppose that immigration increases the labor force by 10%. So we have this inflow of new labor. It makes sense that labor is now less scarce, and so the price of labor is going to go down. Also, with an increase in with an increase in labor, with an increase in input, it's reasonable that your production is going to go up. That's the same thing if you get a bunch of immigration. It's the same thing if you have a higher labor force participation. Your production is going to go up. And then the rental rate of capital, you can think of maybe capital as a complement to wages in the production function. So if you remember complements from intro to micro, a classic complement might be hot dogs and hot dog buns. What do you expect to happen to the price of hot dog buns if the price of hot dogs goes down? So, price of one thing gone down, the price of its complement you would expect to increase. So another way to think about it, that's maybe a little bit easier to think about it, is if labor goes up, it's relatively less scarce, which implies that capital is now relatively more scarce, and therefore it attracts this higher, price for it. So the rental rate of capital has gone up. So yeah, that's the nitty-gritty of solving it and a little bit of the intuition, and hopefully this was helpful. Thanks and have a good day. Bye.